For your attention, the presentation on a topic cloud removal in optical satellite imagery by generative adversarial networks using synthetic aperture radar imagery. In the circumstance of modern challenges to national security, Ukraine needs to improve the level of information and technological support of armed forces. One of the possible ways to achieve this is actively and systematically use remote sensing data. Changes in the methods and forms of modern warfare have led to a significant expansion of the tasks solved with the help of remote sensing data from various medium and high-resolution sensors and their combination. Optical images from satellite provide visual signals that are easily understood by humans, but they are heavily influenced by factors such as clouds, fogs, and smokes. In Ukraine, the average annual cloud cover is approximately 62%. Thick clouds, unlike thin clouds which can transmit, for example, the waves in the infrared spectrum, completely block visual information about the underlying surface. This factor has its most significant impact on the reliability of remote sensing data and leads to a reduction of situational awareness. Thus, an urgent task is cloud removal from satellite imagery in the context of the required continuous monitoring. The purpose of our research is to build a neural network model for reconstruction optical satellite images. The methods for cloud removals that base on traditional approaches can be divided into three main groups. Multispectral approaches are used in the case of haze and thin cirrus clouds when optical signals are not completely blocked. The main advantage is it uses information from the original image and doesn't require any additional data, but they can only be effective with semi-transparent clouds. Multi-temporal approaches reconstruct cloudy satellite images by integrating information from reference images acquired under clear sky conditions. These methods are popular because of their simplicity and practicality. Since they replace cloud pixels with real cloud-free observations, they require the selection of the most recent least cloudy available observations. In case of non-completely cloudless observation at any given time, the resultant forecast will also contain cloudy pixels. The other, correction approaches, fill in damaged fragments using surface information from clear parts of the same satellite image. Some of them don't require additional data but achieve good results only in case of low cloud cover. At current stage of technology developments, methods that use deep learning have become particularly popular for solving the cloud problem. Deep neural networks have great potential for recovering missing information from remote sensing imagery. But an important problem of these considered approaches is demand of large sets of real data. The main common disadvantage is that necessary data sets are very limited. Also, such models focus on narrow areas of the interest and are dependent on synthesized cloud patterns, make it impossible to generalize to more extensive areas and for real conditions. Since the synthetic aperture radar is invariant to daylight conditions and resistant to atmospheric noise but differs in measured values from optical sensors, a new problem arises to bridge the gap between their modalities. Despite the approach of combining optical and synthetic aperture radar demonstrates the possibility of removing cloud cover from imagery, not all spectral features of the land cover can be obtained from the corresponding radar measurements, which fundamentally limits the method SAR to opt. We propose model to reconstruct cloud hidden information from optical satellite imagery is our proposed models combining of existing models with improving by using the next blocks. The model explicitly processes a continuous mask of cloud cover values to preserve cloud-free pixels while correcting for cloudy regions based on the synthetic aperture radar data. The proposed model is trained without strict pixel-by-pixel alignment of cloudy and non-cloudy observation using fine-grained masks with continuous values, unlike the previously discussed models that use binary cloudiness information or are more cloudiness agnostic. The construction of a neural network complies to the architecture of a cyclic serial 7-res next block of a generative adversarial network with two discriminators as the output as follows. It consists of three parts: an encoder, a decoder, and a generator with residual blocks connected by a long skip. Architecture of proposed model shown on the slide. We improve the known approaches to build the model for cloud removal with the residual blocks. During the training, the encoder input includes pairs of synthetic aperture radar, optical satellite images, and cloud masks. The output of the decoder is a map of a predicted cloud masks, and after aggregating the feature maps with the cloudy images, the inverse hyperbolic tangent of slope angle is applied to the cloudy input image before residual mapping to demodulate the effect of the original nonlinearity or on long missing pixels. As a result, when used, the trained model reconstructs a cloud-free optical image. For the loss function, we use the cycle gun approach for both generator and discriminator networks. Losses have been adjusted such that regions regressed as cloudy-free in map remain untouched, while cloudy areas are recovered given information from auxiliary synthetic aperture radar data. For training, the dataset from Sentinel-1 and 2 was used. It consists of globally selected 30-band Sentinel-2 auto-rectified georeference cloud and non-cloud 30-band multispectral images from triplets and the corresponding Sentinel-1 image, its synthetic aperture radar. For evaluation, the following metrics were used. First of all, we used improved precision and recall accuracy and F1 index. Also, pixel level matrix that determines the average deviation between the target and predicted images in absolute terms, and in the units of interest, its mean absolute error and root mean square error. Image level matrix that measures how well the recovered image matches to the original target image in terms of signal-to-noise ratio. It's a peak signal-to-noise ratio. And metrics that quantifies the structural difference between the target and predicted images is structural similarity score. And the last one is measure that quantifies the spectral angle between the target and predicted images by measuring their similarity in terms of rotation in the spectral range space, its spectral angle mapping. During the training of a neural network model, the subsets of 10,000 satellite images from several regions were used as input. Training hyperparameters were set as follows and shown on the slide. The results show that our model is capable to reconstruct cloud-covered areas while preserving information from non-cloudy areas of the image. The proposed model improves image reconstruction by predicting uncertainty and outperforms the considered approach. Also, not all values of the metrics for testing and for evaluation our model were improved in comparison with a known model, but this is consistent with the fact that the proposed loss function involves a compromise between optimizing the mean and estimating the variance. So the experience of the Russian-Ukrainian war requires a qualitatively new information support for the armed forces of Ukraine. The main way to improve it should be the use of commercially available medium resolution satellites. The cloud cover on satellite imagery prevents the full use of remote sensing data, or it seriously affects the time and spatial availability of the observation of the on the Earth's surface. The additional information contained in the synthetic aperture radar input data is useful for improving the reliability of image reconstruction. Our proposed attention-based neural network is tested on the real dataset. Comparison of the obtained result with existing model demonstrates the possibility of its application for image reconstruction during the pre-processing of multispectral satellite images data. Thank you for your attention.